All right, we'll go ahead and get started with the introductions. Welcome everyone to the University of Connecticut Brain Imaging Research Center speaker series. So this is something we've been doing for a while, about twice a month. Of course, we're doing it virtually now. So we've had a fantastic lineup of speakers, some of which you can see here on the screen. And our current format is that people tag the next speaker. So our previous speaker, Roshan Kuhls, tagged Tim Behrens, but Tim actually passed this on to one of his fantastic students, Yunzhe Liu, who'll be talking about his work in memory representations. But Tim will be doing Yunzhe's introduction. To get more information about the speaker series, be sure to check out our website. That's berk.uconn.edu, and look on our news and events page for the upcoming speaker schedule. And we also have a listserv where you can get these talk announcements. So please sign up for that. So please stay muted during the talk. We'll have about an hour for the talk and then some time for questions afterwards. If you do have questions, you can put those in when you think of them into the chat window, and we'll get to those at the end. If you do have a kind of immediate clarification question, you can go ahead and interrupt to ask that, but otherwise we'll try to keep questions for the end. Okay, so I'll just briefly introduce Tim Behrens. So Tim is the Deputy Director of the Wellcome Centre for Integrated Neuroscience at Oxford, Honorary Lecturer at Wellcome Centre for Imaging Neuroscience at UCL, and Wellcome Trust Senior Fellow, and Deputy Editor at eLife. So he got his PhD in Information Engineering from Magdalen College at Oxford in 2014. And I believe he is very recently a Fellow of the Royal Society. Congratulations on that. With that, I'll hand over to Tim to do the next introduction.
Thanks, and thanks for inviting them. I'm pleased that Roshan tagged me. I think this tagging idea is great. However, so Zoom has made it a bit mad, really, I think. I feel like people like me just get invited to talks a lot on Zoom because we can't really say no. And we can't say, oh, it's a bit difficult in my travel schedule, all that kind of stuff. So I feel like I've given more talks since lockdown than ever before. And actually you can, because they're all recorded, you can see most of them on the internet. So if anyone did want to see me speak, then they can just go and look it up. And so I feel that I should be not accepting new invitations to give talks, but trying to get more junior people the kinds of slots they would have got in the past. And so one of those amazing junior people who's worked with myself and Ray Dolan is Yunzhe. Yunzhe's remarkable. You'll all know how remarkable Yunzhe is by the end of this talk, because I think he's going to present to you a whole bunch of remarkable data, things that you might not have thought that you could do in humans. I think Yunzhe is going to be presenting. And I could give you a whole list of his other achievements too. His work before he ever came to UCL was already totally ludicrous in quality and quantity. When he was a master's student, he was writing neuron papers and things like that. And Nature Neuroscience papers, but since he came to UCL, he's won Best Student at UCL prize, which is no mean feat in such a massive neuroscience institute. But I think that the best praise I can give to Yunzhe is this thing you're about to hear is really him. It's not us, and it's him in many different ways in terms of the contribution. So it's a technically hard thing that he's done, mathematically complicated to work out how to measure these things, and that's Yunzhe came to UCL as a psychologist, and he leaves as a machine learning expert. And then the conceptual neuroscience ideas are intricate and interesting in this piece of, in the work that you're about to see. And again, that's really all Yunzhe. Really one of the most extraordinary students I've ever worked with, from every angle, every skill that you could need, or every piece of imagination that you could want, you'll find in Yunzhe. And so I think you should have fun in the next hour, and so take it away, Yunzhe.
Yeah, thank you very much, Tim. You almost make me cry. I'll try to do my best. So let me just share the screen. Okay, great. Can you guys see the screen? Can you guys see the screen?
Yes, I think we can see that. Good.
Cool. Yep, great. Yes, thank you so much for the invitation, and thank you so much for the very kind introduction from Tim. So it really has been a really great 4 years of work. So today I'm going to talk about two major projects in my PhDs. In my PhD, and one is about, so all of them is about this internal computation that we do during rest, and that's I hope I can convince you in the end of this talk that this offline activity is actually really important to our cognition. And today I'm going to talk about two projects, one related to inference, another is related to learning. Okay, great. So the first thing I want to talk about is a very particular question. So now imagine if you are this rodent, and the only thing you want in the world is this piece of cheese. Now, let's imagine this is the first time you have ever entered this room, and you have no clue what you should do. Now, you probably need to take a squirrely path in order to get the cheese. But when you get it, this is your first time to find the cheese. But when you get it, then the next time when you enter the same room, of course, you can do the same thing again, right? Because those actions are good because it leads me to the reward. However, if I'm smart, if I understand how the space works, I can really just take a direct path, and that would take me directly to the chase. And this is the question I want to understand. That is, how in our brain, what kind of computation is happening in our brain that allows us to do something like this? So to frame that in another way is, if we know the relational structure, then you can make inference about the things you haven't seen. And how the brain actually implements those kind of computation is one of the intriguing ideas and questions I want to answer. Okay, great. Sorry. And then there is one pretty remarkable phenomenon that has been documented in rodents. So we all know in rodents, in hippocampus of the rodents, we have those very special cells, we call it play cell, that's normally only going to fire at one given position of the maze, right? So for example, let's say each of the color indicate where the rodent is, and it's blue gradually to red. Each color indicate one given position. And when the rodent is doing rest, like sleep or something, sometimes if you measure the background signal in its hippocampus, you sometimes can say these very rapid oscillations. And if you measure the multi-unit activity, like all spike activity, if you add them together, you will see a huge deflection. That means at that time, a lot of neuron is firing all together. And this is time we call shape wave ripples. And in those time, a lot of those play cells are going to fire rapidly. But what is really remarkable is that during this time, those spontaneous firing is not random. Normally, it has certain structures. For example, it might respect the order of the experience. For example, it might go in the same direction as the experience, as depicted here, from blue gradually to red, for example. And because it's a tempo sequence, not only can it encoding representation content, it also have direction. So we can call the same direction of the sequence as the forward sequence, the same direction with experience. And we can call the backward sequence, i.e. the opposite direction with the experience, as a backward sequence or backward or reverse replay. And this direction have quite an intriguing property. For example, let's say I put a trace in the end of the track, and if I increase that amount of trace, i.e. reward to the rodent, and then what will happen is you will only see selective increase in the strength in the reverse replay, but not forward replay. It's intriguing because this is actually implicit in reinforcement learning theory. So here is the idea that if you have a choice that go left or right, and let's say in the right path, you get more reward than you expected, then because you're making a critical decisions in the junction, right? So either go left or right, but you only get a reward in the very end of one of the linear track. So the job in your brain is trying to backpropagate that reward signal back to the place where you need to make the decision, right? And so therefore it's intriguing to think about this reverse replay actually is doing this credit assignment thing that is trying to link the outcome and then the actions, and then trying to link it by using temporal sequence to linking both space and time. Cool, so this happens during rest, and it seems to have very interesting properties. And because I work in humans, and a logical prior for anything I want to do is I have to answer this, right? Can I find replay in humans? So this is quite complicated question because in humans, it's normally not the case. We can always stick a needle in their hippocampus or in other brain regions. Normally the best we can do is to put them in a giant machine like EEG, MEG, or fMRI, trying to measure the whole brain signal. But the question comes, can we still measure this fast, spontaneous neural activity that we presumably think it originated from hippocampus based on the research from the rodent literature? So how to measure replay in humans? So what I'm trying to do here is to using MEG. So for people who don't know MEG, it's quite similar as EEG. It's trying to measure the magnetic field generated which is associated with their neural activity, and it is measured at the scalp level. So the good news for that is this is a whole brain neural activity recording. But the bad news is we will have quite a low signal to noise ratio compared to like electrophysiology that we have access to in rodent research. Okay, then what do we want if we want to measure replay in humans? And the idea is like this: we want to measure replay or the transition or the sequence in a quite abstract relation graph. For example, here each of the S indicate a state, and each of the lines indicate a transitions. And let's say I want to say during rest, can I say structured transitions from S1 to S2 to S6 and then to S1 again? This is quite a hard question if we want to using existing rodent method to do. Because normally in rodent method, what people trying to do is measure the relationship between time and space, which is normally fine, right? Because if you only look for linear track, like how then the position, the decoded position is normally correlated with the time, and they can take advantage of that. But if we want to look for any transitions in any arbitrary graph, we will not have that property to take advantage of. And what should we do? We should translate those time by position metrics to a state-by-state transition matrix, and then we can define our hypothesis in relation to the transition matrix and look for evidence of that in the data. And here is how we do it. So it's a three-step technique. So the first step, we're trying to get the state representation. We can use either encoding or decoding model, trying to get a multivariate representation for each of the state. And here state can be indicated by visually evoked new response from certain stimuli like face, house, or tree, for example. And then in the second step, we can apply those classified during resting time, and we can get a time by state matrix. Then we can do this thing we call tempo-lagged, tempo-delayed linear modeling, i.e. we regressed a lot of time point lagged by a certain time and regress onto an earlier time point. The idea is trying to say, does the later time point can predict a later point in another state while controlling for all other states, right? Because when we do that, we can also, in addition to gradual causality, some people know, we can also control for autocorrelation in the state. And then after we do that, we can do that at each of the time lag, i.e. the time lag, we can think about time lag as speed. So the shorter the time lag, the higher the speed is. And then we can measure the sequenceness, the evidence of sequence as a function of the speed. And then we can test at which speed do we have the maximum evidence for the sequence going in the direction we care about, like here, beta 1, 2, 2, 3, and 3, 4. So here is the transition matrix, right? So each of the entry indicate the transition strength from state 1 to state 1 here, this state 1 to state 2, for example. So this is the second, so this is the step 2, that we quantify the sequence strength as a function of speed. And then the third thing, we should do statistic inference. And the way we do it is we redo the whole thing again, but we randomly shuffle the state identity, i.e. the null hypothesis is all the state identity are exchangeable so that we can test whether we have more sequence of 1, 2, 3, 4 compared to random, for example, 3, 8, 7, 4, for example. And we can do that across all time lag, trying to control for multiple comparison. We can also do that separately for forward direction and backward direction. Like here, 1, 2, 2, 3, and 3, 4 in red would be the forward direction, so to speak, and then the backward would be beta 21, 3, 2, and 4, 3. So we are going to show this plot aloud. So it was to spend some time on that. So here, the x-axis is not time, it's a time lag. It means the lag between each of the state. For example, here in this simulation, it means state 1 is followed by state 2 by, for example, 40 milliseconds. Okay, so the time lag indicate a speed of the sequence. The shorter the time lag is, the higher the speed is. And this dotted line is the permutation threshold, which is taken as the 95 percentile of the maximum sequence you can ever find across all time point, all time lag we have tested in the permuted samples. And the y-axis would be indicating the sequence strength. And sometimes we might do forward minus backward, which would give us a secondary statistics. It tells us at each speed, do we have more forward than backward, or vice versa. And here is the approach we're going to use throughout this talk. Cool. Feel free to ask me any questions. Cool. I'm going to continue and pretend it's super clear. But yeah, feel free to interrupt me if you have any questions. Great. Cool. All right. So the first question I want to ask is, can replay reorganize experience for efficient inference? That is the first thing I want to answer. During rest, does replay simply recapitulate what they have simply experienced, i.e. is literally replay? Or does replay actually reorganize experience into a meaningful and coherent order that is useful for me in a later task or for my later calculation, for example? And in order to ask this question, the key idea is I have to make a contrast between the past experience and what it should be look like based on some structural knowledge. So here is the example. So for example, this is a quite standard experience. For example, your friend tell you, like pre-COVID time, he tell you he woke up in the morning and he wait in a queue, and then the reason he wait in a queue is because he entered Starbucks and then he got a coffee. And he told you he need to first pass the door in order to wait in a queue. The way your friends tell this story probably is quite disorganized, but you can still figure out what is the experience your friend had, right? And the reason it can happen is because we have those prior knowledge of what this kind of daily experience would look like. And what it's saying is, if I know the structural knowledge, I can reshuffle the experience I just had or information I just received and reorganize that into a coherent and meaningful order. And this is essentially what I want to test. That is, does human replay during rest that only respecting the visual experience, or is actually respect the true sequence, i.e. the sequence identified, defined by the structural knowledge? Okay, the key thing is I'm going to asking the participant to learn the scribing rule. That is, which picture should be put in which place the day before the main task. So this is the structural knowledge they need to learn. And critically, we ask the participant to learn this knowledge with a different set of stimuli. So anything they can do on the main experiment day is trying to generalize some abstract knowledge they have learned the day before to the current day. Great. So in day one, we do this training, and this training looks in this way. So we train them in this like disrupted order, right? And then we tell them what is the mapping from those disrupted order to the true order. And those transformation is what they need to learn during the day one training. Like for example, here in this experiment is quite simple. That is, the thing connect to each other is important conjunction. For example, the door, because the door is a common node, so you need to link the Starbucks door and the queue together. And then the clerk is one of the common node, so you need to combine the queue, the clerk, and coffee all together. And then you can combine two things together to figure out the whole sequence. Okay, we can express that in this way, right? So red, green, yellow, red, and green, blue. We can link them based on the common node, which is yellow, red, green, blue. All right, and on the second day of MEG, what we're going to do is first we're going to show them the picture they're going to say on this day. And we call this functional localizer, which we're going to use that to train their representation for each of those pictures. And then after that, we do this phase we call applied learning. In this phase, we're going to ask them to view those pictures in those disrupted order, but because they know how to transform those visual sequence into true sequence. So like here, right? Then during rest, I'm actually testing that. So during rest, the participant doesn't need to do anything. And after experiment, I'm going to test, does the replay follow the transition of the visual experience or the true experience or the true sequence, so to speak. Okay, so, and after that, I'm going to introduce this session we call value learning. We have two sequences, and I'm going to randomly select one of the sequence and pair that with reward. And the idea is, for those rewarding sequence, they should update the value for each of the state in that sequence. And I want to test, when that happens, do I see more backward replay than forward, as is the case in rodent literature? Great. So I'm going to test that in the second resting state, where there will be one rewarding sequence and one neutral sequence. Cool. So the first things first, we want to see whether we can actually identify replay. Oh, sorry, whether we can actually identify those pictures, right? Because those pictures are going to use to index state. And during rest, we are actually looking for their sequential reactivation. So the logical prior here is we have to decode those states. Okay, so here, what I'm going to show you is temporal generalization plot. So on the x-axis is the time that I'm testing that. I'm testing the classify, and then the y-axis is the time I'm training the classify. So I trained at each of the time beings and test on all time beings. And I do that from the 10 millisecond to the 1 second. Then I have this temporal generalization plot. You can see a very strong diagonal component. If I take that diagonal, you can say it peaked around 200 milliseconds. And I can actually train my decoder at the peak accuracy time. And if I do that, I can do that for each of the picture. And if I do that, for example, if the true picture is stimulus 8, only the stimulus 8 classify give about chance classification accuracy or readout. The dotted line is the permutation threshold, and everything else just below it. So this trying to show we have quite good specificity of the decoder we have trained. And we can do that for each of the stimulus in a cross-validation way. And if we do that, we can show for each of the pictures, we have quite good specificity, i.e. only the true labels, only the classifier of the true label give about chance reactivation, while others doesn't. And there remains quite a similar range. And because it demonstrated we can decode the picture quite well, and then the next question we're going to ask is, can we see those things reactivated in certain order during resting state? Okay, so we first test, do we see evidence of true sequence? Now, again, x-axis is the time lag, it's not time, this is the speed. So y-axis is the forward minus backward. So anything above 0 would be forward stronger than backward. Anything negative would be backward stronger than forward. Now we can say we have strong evidence for forward stronger than backward at around 30 or 40 milliseconds. Noted again, this dotted line is the permutation threshold. Anything exceeding that would be significant. Okay. Now, we can do the same thing for the visual sequence. And when we do that, we see diminished evidence that it doesn't pass the permutation at all, which is good. And now we can say what it looks like. So we have two studies. Now we can just focus on the first one. So we can, because we know when does replay happens, i.e., sorry, we know the optimal speed of that replay happens. So we can back project that time lag into the data, trying to figure out when does replay happens. When we figure out when does replay happens, we can just analyze the resting state data as like task trial we normally do, right? We can just epoch the resting state based on the onset of replay, and then we have sets of replay events. And then we can just do tempo frequency analysis on those candidate replay events. And when we do that, we see a quite sharp increase in the high frequency from 120 to 150 hertz. And that's normally what people call sharp-wave ripple or ripple frequency. And you can see this can be replicated in a study 2, which I'm going to talk about later. And what is interesting is, so previously I'm looking at the tempo frequency across all sensors. I can also do that separately for each of the sensor. And here I'm showing you the sensors give me the significant results of those sharp-wave ripple frequency power increase. And those distribution is quite remarkable, because if we reference this with a study where the author did simultaneous recording of intracranial EEG recording in hippocampus with MEG, we see, so those are the sensor distribution show significant correlations with hippocampal activity. And you can see it looks quite similar as our studies. So this is an indication that what we have found perhaps really is, or maybe is a reflection of the hippocampal activity. And then we can try to do a beamforming, which is a linear transformation. where we only look at the ripple frequency at the onset of replay, we can say at the whole brain level, it has localized to the hippocampus or to MTL, medial temporal lobe, if we're trying to be like more precise about this. I'm trying to make, yeah, cool. Now, I have told you before, we have two resting, and in the second resting, the two sequence has changed its meaning. So one of the sequence become rewarding sequence, and another sequence become a neutral sequence. And during this second resting, I can ask, does the rewarding sequence involve a specific change of their reverse replay, as you would expect from the Dolan literature? So again, there are two sequences. One sequence is to reward, and another sequence doesn't. If we look overall sequence, we see a strong backward sequence, again, around 30 or 40 milliseconds. And we can also assess the strength of the transition. So length 2 would be AB, length 3 would be ABC, length 4 would be ABCD. So we do all those analyses by always controlling for the evidence for the short transitions. So the significant results in length 2 does not contribute to the evidence of length 3 or length 4. However, even we control for that, we still have significant evidence for that, which is really showing we have quite a strong backward sequence linking from the end state where it is paired with reward all the way back to the initial state. Yep, and we can look sequence separately for each of the sequence. And the idea would be only the rewarding sequence should change its direction, but the neutral sequence shouldn't. And this is what we find. Only the reward sequence after value learning changes the direction from forward to backward, whereas the neutral sequence, if anything, is still dominantly forward. Now we can do something similar as we have done previously. We can contrast the onset of replay between the reward sequence and the neutral sequence. And when I do that, I see a strong increase in the VMPFC and it extending to striatum. Although again, because it's MEG, we have to see it with caution. It's suggestive, but we don't know whether it is true or not. But nevertheless, it's quite intriguing. It coincides quite well with our FMI literature, where the VMPFC or striatum is encoding reward or value. Great. So for this study, it seems we answered the first question. We definitely can find a neural replay in humans. And the second question is actually, if you really think about that, it's not that straightforward, right? And the reason is like this. If you have remembered, I previously told you the restitching rule is trying to find the common node and then stitching things together. This sounds quite similar as Hebbian learning, right? We just need to find one common node. You can think about some variant of the Hebbian learning rule that can allow you to stitch things together in a pure associative learning way without any structural knowledge, right? So we don't really answer the second question, and we have to, because everything can be done implicitly. They don't need to encode the structural knowledge. They can simply just do associative learning in principle. So I want to answer the second question in a more thorough way. And the way to do it is I should even scramble the pairwise associations. This is the key thing. This is the thing that has not been scrambled in the first study, right? So AB is always linked to AB, both in the visual sequence and in the structural sequence. But maybe BC has been disrupted, but not AB. So that is the casing. And then I want to understand if this replay is not formed by associative learning, then how does it come from? Our hypothesis would be it is being guided by structural knowledge. And in order to test that, we have to get a new readout of the structural knowledge. And those two questions is what motivating us doing another study for this project. So in this study, what we are doing is we're going to even scramble the pairwise transitions. Now, think about this scenario. even you have even crazier friends that tell you a story in an even more jumbled way. For example, if he says something like, I wait in a queue someday, and I see a Starbucks brand, and then I see the clerk. I give her my credit card. Oh, before that, I walk into a door, and in the very end, I get a coffee. Oh, I walk. The reason I can do all that is because I get out of my home today. So this seems quite strange, right? But you can still, somehow you can still rearrange it and figure out what is the true sequence is. Your friend sees the brand of Starbucks, get into the door, waiting in the queue, see the clerk, and get the cup of coffee, right? And the reason you can do that is because you roughly know, like, in which position and in which order those elements of experience should happen, right? So, for example, the Starbucks might happen in the first position, and then the coffee, which could be the outcome, might happen in the very end. And because you roughly know the order of each element of experience, so you can rearrange any of those kind of experience into a coherent order, right? And we can take advantage of that. We can actually train the participants those mappings, i.e. the visual presentation order of the element of the picture, and then the order of that picture should appear in a defined sequence. And if we have that transition, have that mapping in mind, then we can transform any picture into a coherent story just based on the learned rule. Yeah, so this is what we're going to do in study 2. And then, because I want to get a structural code, so I designed the experiment specifically, it can be perfectly described in 2 coordinates. One is the sequence identity, sequence 1 and sequence 2. Another would be position 1, 2, 3, 4. And this 2 dimension can give me a unique position for each of the pictures. So we can say it has a structural code that have 2 axes. One is sequence identity, one is the position location. And then in the very end, after they have figured out which picture should be put where, I can simply ask them. Like, I can present those flower picture and ask them one of the 2 questions. For example, which sequence does this picture belong to? For that, I can get the sequence code, i.e. the sequence identity. And another question I can ask is which position does it belong to? And for that, I can get a position code. And those 2 things would be orthogonal to each other because those 2 things are independent orthogonal dimensions. Okay, cool. And then, because I have the hypothesis, we have the hypothesis that it is really the structural knowledge that really guiding my sensory information to replay in the right order. And for that to happen, my hypothesis would be the structural knowledge is learned the day before. So I need to test that, i.e. before they have seen any picture, could I say certain representation of the structural code? And does that actually already play out in a structured sequence? So that's what we're going to test. We call that transfer replay. Transfer, i.e. transfer the structural knowledge learned from the past experience to the current lower context. Okay, so the way we do that is still quite similar as study 1, but the crucial change would be first, we add this resting state even before the functional localizer on the 2nd day of the MEG study. So this is the time that is even before they have seen any picture they're going to say in this experiment. So we are going to test, do we say some structured sequence of abstract code that is independent from the sensory code? And in the very end, when they have learned those 2 sequences, I will try to get that structural code, i.e. there are 2 dimensions, the sequence identity and the position locations. Yeah. Cool. And then after the functional localizer, same as study 1, I will do applied learning where the picture has been totally jumbled. You can say D prime to B where there's no relation at all. The only way they can figure out from the visual sequence to true sequence is remember the mapping. the mapping, for example, the first picture have to be put in the first position of sequence 2. The second picture have to be put in the second position of sequence 1, for example. Okay, and then after that applied learning, I will put them in rest again. And during that rest, I'm going to test the sequence the replay is following. Does it following the visual sequence, or does it follow the true sequence? Yep. And in the very end, we do this sequence position testing. This will be used to get their structural code. Cool. The first thing we can look for is direct replication of study 1. So yeah, it seems we can replicate study 1. We say a similar forward sequence in a similar speed, around 30 or 40 milliseconds, and that is respecting the structured true sequence. And if we look for sequence of the visual transitions, we have no evidence. So that's good. That means we have replicated study 1. That means the thing we have found in study 1 is not really due to implicit learning, or put it another way, this suggests we at least have additional mechanism to achieve that. Yep, and the second thing I want to say is, can we actually read out the structure code, right? Because I want to understand if replay doesn't happen because of the associative learning, how can replay happen? And the idea of our hypothesis would be is actually guided by the structure code. Yeah, to test that, just to remind you, we have 2-level experience. One is the sensory information, one is the structural information for each of the picture. And for each of the picture, the structural representation can be further separated as the sequence identity or the position location. Yeah, those are 3 types of representations. The first thing I want to show is we can actually get all 3 types of representations. Okay, the first thing is sensory code. We can just do the normal cross-validation thing, right? We just leave one stimuli out, and to say the classify train on all training examples, would that generalize to the left outer stimuli? And it seems it does. It also picked around 200 milliseconds. And then we're trying to do for the structural code. This is slightly complicated, right? Because every time when we're trying to decode the structural code, the picture is on the screen. And because it's a decoding model, we don't really know which feature it latch onto. So the way I do cross-validation is in a different way. For example, if I want to get the position code, like position 2 code, I can take the advantage of the design that I have 2 sequences, right? So I can train the classifier on the one stimuli in position 2. Let's say the stimuli from the sequence 1 in position 2. And after I have trained that classifier, I can test that classifier on the picture, on a different picture, which is also in the position 2, but it's in a different sequence, and it's a different stimulus, right? And because of that, anything about chance decoding accuracy can only be due to their shared structural representation, and here would be their position representation. And the same logic can be applied to the sequence code, right? You can train the sequence code by using pictures in the same sequence. For example, position 1, 2, 3 pictures in sequence 1. After you train that code, you can apply that to a different picture. For example, the position 4 picture in the same sequence. Again, it's a different sequence, it's at a different position. The only thing is the same, is they are in the same sequence. So anything about chance has to be due to they have actually can read out the common structural knowledge, i.e. sequence knowledge here, and here would be the position knowledge. And again, if we do that, in a temporal generalization way, we can say the sequence code pick around 150 milliseconds, and the position code pick around 300 milliseconds. And we can try to train those code in those time points. After we have done that, we can apply all 3 code all together at the applied learning to say at the time when they need to arrange a stimulus into the right order, do I already have the evidence of the structure code? It seems we does, and we say they are actually independent. We can independently decode each of them. right? It says they at least have some factorization going on, i.e. there are some independent components between them that allow me to read out some of the component of them separately. So for example, when they present with the fate, the green tell me this is the fate, and then the red thing tell me put that in sequence 1, and then the red thing and the blue thing tell me put that in the position 2. And all those three information combined would tell me uniquely which position does this picture should be put to in that 2x4 axis dimensions, right? Yeah. So what does it show you is when they say the stimulus during learning time, the brain already codes the structural information. Okay. It seems we can read out structural information. It seems it's already there during learning. Now the question becomes, what happens during rest? How does replay follow the structural sequence? And here would be the summary I'm going to show you. So here, the x-axis is time. So this is just illustration. And then the y-axis is a different code. Sequence 1, 2, position 1, 2, 3, and stimulus 1, 2, 3, 4, all the way to 8. And the summary idea would be the structural knowledge, which is the sequence and position code, activated at the same time. And it activated always before the relevant stimulus time. And it is the relevant position information leading the relevant sensory information to replay in the coherent, meaningful order. Okay, so this is a general idea. And now I'm going to show you how I test for that. So notably, one way we can test that is actually using exactly the same technique, the sequence detection technique we have developed, right? We can look for the transitions from sequence 1 to stimulus 1, from position 1 to stimulus 1 versus stimulus 1 versus position 2 to stimulus 5, for example, right? And if we do that, we can say the position code is actually leading the relevant stimulus code, like around 40 milliseconds. Yeah. So here, the meaning here, this if it's positive means the position code is leading the relevant stimulus code, and if it's negative, it means the other way around, i.e. the stimulus code is leading the position code. And we can use the same thing for the sequence code. Again, we say the relevant sequence code is leading the relevant stimulus code. And then we can look for the evidence of sequence code and position code altogether. And you can say they actually happen at the same time. So just to remind you, this is a time lag, right? So because it's picked at the very first time lag, that indicates the strongest correlation happens at the 0 time lag, which is simply just correlation, which we call that zero lag correlation. That means they happen at the same time. There's a low lag between them, basically. And we can actually test that by randomly shuffle it. And you can say it is well above the shuffle distribution. This is suggesting indeed the position code and sequence code, which all belong to the structural knowledge, all reactivating at the same time. And they are guiding the relevant stimulus time into the right order. And we can even test, because the position also have a sequence, does the position code actually replay in the order that guiding stimulus to replay in the right order? And we can say it's indeed happening this way. Cool. So here is the summary. We show the replay generalized structure to Liu experience through this factorized representation. All right. Now we can, in the very end, we can test this very first idea we have, right? We think it's this abstract structural knowledge that is guiding the sensory information. And for that to be true, notably, this structural knowledge is already learned the day before. So if that is indeed the case, we should be able to read out those abstract code even before they have seen the stimuli. And this has some interesting similarities to the idea of pre-play in the rodents, where Tanagawa group have reported that before the rodent enters the maze, you can already detect some replay signal in their hippocampus that depict the trajectory they're about to take in the future. And one intriguing idea we have would be those things might be constrained by their structural knowledge because they are linear, they're all linear track, right? Those general statistics might already put a prior on what kind of sequence you can go to. And that might already being played out even before you enter a specific maze, for example. Okay, to test that, remember we have the position code, and we can direct test for the position code in the first resting, right? And we can say it's go backward and it's significant, sorry. But we can also try to be precise. We can do a sanity check. We can say the stimulus code doesn't play out, which makes sense, right? Because they haven't really seen the stimulus at that time. We can even regress out any stimulus code that can be explained, and we can regress out the stimulus code from the position code and apply the residuals, which is anything that left out after the regression, to the first resting state. And we find the similar picture, i.e. really is those abstract structure code, which is independent from the stimulus that already is replayed in the right order. So this is saying we have those kind of abstract knowledge. It says it represents those relational structural knowledge explicitly prior to the experience of stimulus, right? And now we can really test this idea during learning, right? So the pre-play, you can think of that, the reactivation of the pre-play, you can think of that as a strength of their abstract knowledge. And the idea would be if you have more preparation of more stronger prior, you don't need that much of data to convince you where you should go, right? Indeed, you should say elective correlation for how strong your prior is and how much data you need in order to reach the same conclusion. And this indeed we find. So we can operationalize the learning as the reactivation amplitude of the position code during the applied learning. And we can say they are electively correlated. So this is suggesting the pre-play of the abstract structure code actually facilitate Liu learning. All right, so here is the interim conclusion for the question 1. So it says we can measure, across 2 studies, we show we can measure replay in humans. And as in rodents, human replay occurs during rest, reverse direction after reward, and also similar as rodent, it coincides with hippocampal shaft retrievals. But what's remarkable and what's unique with human replay, as we have identified so far, is it actually reorganizes experience based on learned rule, and is factorized. Its representation is factorized. You can separate structural abstract knowledge with the sensory knowledge, and that separation allows fast generalization of structural knowledge to the current lower context. Cool. So this is the first study. Any questions? Cool. So if not, I'm going to continue to the second question I want to ask. So the first question really trying to ask, does replay reorganize experience for efficient inference where everything is already learned, right? You just need to apply the knowledge you have learned to the lower context. And then the second question I want to get at is how replay actually help learning, like learning on the fly, for example, and especially for long local learning. And why long local learning is important? That is because normally the action and outcome are separated by both time and by space, right? Both by time and space. For example, if you are playing chess or play Go, you don't really know whether your current action is good or bad, unless 1 or 2 hours later, when you see the final outcome, whether you win or not. And even you have seen that outcome, you still have to decide a way to contribute that outcome to each of the action, right? This is quite a hard problem. This is a problem we call credit assignment, which is a very active research field in reinforcement learning. And people study that from different perspectives, like computer science, neuroscience, psychology, etc. And this is a question we're trying to get at the brain level. I want to ask, how does the brain implement a long local learning algorithm? And would replay be the mechanism that actually help bridge the time and space which makes sense, right? Because replay is a temporal sequence. It happens very rapidly. It can represent a lot of offline representations. So it could be a perfect candidate that bridging the separate space and time between action and outcome. To make that more concrete, so this is a problem of real life, right? So imagine again, you are this rodent, and the only thing you want is this piece of cheese. But in the real life, there may be many ways that leading to the same outcome or to the same state, right? For example, you can start at yellow, green, and blue, right? And now, for example, now this time you start at blue, and you take the left path, and you get a trace. Great. However, if I know the other road is also leading to the trace, then that would be even better, right? Because then the next time, if I've been put in the yellow position, I know I should take the right positions, take the right actions, because that will lead me to reward. And this outcome is separated from this action, from this state, and this is what we call non-local. So, and this is a problem of credit assignment, i.e. how you bridge the time and space between action and outcome. And how can I solve that? There are two separate inquiries, both in reinforcement learning and in neuroscience, suggesting replay might be a way to do that. So in reinforcement learning, the replay would be to randomly sample an experience from my memory buffer. And in the neuroscience, the replay is what we have been talking about, that we say replay go in direction in hippocampus that recapitulate past experience. And this is a question we want to ask. Does replay actually help solve those credit assignment problem, which has been long hypothesis, but has never been tested or linked to behavior change? Okay, great. So this is the breakdown of the problem. So because I care about a non-local learning, so I have to separate local and non-local, right? So the idea is this. If I, at the blue location, if I take the left path, I get the trace. And this would be local learning, right? I can do that through a model-free mechanism. I can just do that through trial and error. I do left, I get a reward. I should repeat my action, right? I don't need to know the transitions, the relations between different actions at different outcome, because I can simply just do model-free trial and error learning. But if you are smart, you can do non-local learning, which does require a model of the transitions. You should know, for example, this trace can be reached from different of the state, and each of the action in each of the different state can lead into the same outcome, right? So when you add the blue, and if you take left, get the trace, you should also update the relevant actions in different initial state, right? So this is the problem we call non-local learning. Yep. And if there is indeed a non-local learning, then a secondary statistics come along, which is given limited time and resource, which experience should I prioritize, right? Because imagine in real life, there are so many experiences that perhaps have a similar outcome. Which experience should I put more priority on? Would be another problem if I want to behave optimally, right? And luckily, Marcello Matter and Nathaniel Dahl have provided a very interesting and intriguing analysis purely based on reinforcement learning. So it turns out if you extend the one-step MDP to multi-step MDP, you can rewrite those questions as an equation as the expected value from replay that experience actually equals to a product between need and gain. And need is indicating how often I will encounter this experience again in future. And gain would be how much actual reward can I achieve by replay that piece of experience, right? So it have quite a interesting similarities to this idea of decompose your Q value into the reward function and the successor representation. But I'm not going to talk, going more than that. So again, I should say this is a close collaboration along with Tim Behrens, also with the group in Princeton, i.e. Marcello Mata and Nathaniel Dahl, and it really is a quite fruitful collaborations. Okay, great. So here is the task design. So again, just very similar to the example I have introduced, right? So we have 3 arms, and each arm you have 2 paths you can choose from. And crucially, each of the arms have 2 outcomes, and those outcomes are shared among all 3 arms, right? So this allows me to separate local and non-local learning at a trial-by-trial basis. And then to answer the secondary statistics question, i.e. prioritization, what we did is we manipulate 2 things, lead and gain. So the lead is manipulated in the model learning, where they have learned, each of the arm will have a constant and fixed starting probability. For example, the blue one, you would more likely to be put in this arm 50% of time, and 33% of time in the yellow, and 17% in the red. So this is not chosen by the participants. This is designed by the experiments, by the experimenter, right? So those indicating how likely you're going to encounter each of the experiments in this task. And this is not chosen by you. This is certainly fixed. And the only thing you can do is, after you have been put in certain of the arm, you need to select the path that you think going to lead you to the reward. So X and Y will have binary reward, and their reward probability is fluctuating gradually over the trial. There are 300 of trials also, and they are independent. So, so any information you get from X doesn't tell you anything about Y. So that makes this really a 2-armed bandit task. You have just to learn the value for X and Y separately. Yeah, and this reward manipulation would be a manipulation of the gain, i.e. how much actual reward I can gain by replaying that piece of experience. Good. Great. Yeah, and this priority is defined as gain by lead. And for this study, what I really want to get at is this triangle, i.e. priority, replay, and behavior. Cool. The first thing, what is the model-based behavior here? So here the model-based behavior is actually quite clear, right? So the local learning would be an index of model-free learning, right? Because if you are starting from the same arm, are you going to repeating the same action if you get a reward versus not getting a reward? And a non-local learning would be a marker for model-based learning. For example, this time you're starting from the blue, right? And you get a trace. And the next time, if you are starting from the yellow, if you are model-based, you should more likely to choose the path here that you know going to lead you to the chase. And the reason you know that is because you understand the relational structure in this task. That is, this path, which is leading to the chase, is shared among all 3 of the arms, right? And we can test that. We can test that in a purely model agnostic way, i.e. what is the probability you're going to choose the action that leads you to the same outcome, depending on whether you are starting from the same arm or a different arm, or whether you get a reward or no reward from the last trial. And we can do that. So the same R indicating you are starting from the same arm compared to the last trial, and you get a reward last trial. And the same R versus same NR means no reward. Those would be an indication of model-free learning, right? And we can say it's highly significant. And the diff R indicating you are starting from a different arm compared to the previous trial, and R again indicating you get a reward. And this distinction will be a marker for non-local, i.e. model-based behavior. And we can say we have very strong model-based behavior. And it's also interesting that those model-based behavior is actually quite similar. The degree of which is quite similar to the model-free learning. That is saying the participants in our task really have very strong tendency to be model-based, which is good, right? Because we really care about to link replay to non-local learning, which by our definition has to be model-based. All right, the first thing is purely based on the behavior modeling, we want to ask this question. So first, there is no differentiation of model-free and model-based learning. However, we can still look for some prioritization only in the model-based learning, i.e. non-local learning. We can separate non-local learning based on whether it's this path is high lead or high gain versus low lead or low gain, right? We can use different learning rate to indicate that, and we can compare the different learning rate. And when we do that, this is the question we're asking: does we have a higher learning rate for high lead or high gain arm, or yeah, exactly, for the high lead or high gain arm versus low lead, low gain arm? Yep, and when we do that, we indeed see significant results. So this established one line in this triangle, i.e. we do say the behavior is prioritized according to this normative model. Okay, the second question is we want to turn to the neural data, because the core question we really want to ask is how the brain implement this non-local learning algorithm. And again, the first thing is we have to show we can decode those pictures. And in this task, it's non-trivial because we have all 18 stimuli we need to decode, right? Because we have 6 sequences. Each sequence has 3 stimuli, and they are all distinct visual stimulus. And when we do that, we say, okay, fine, we can decode them quite well. We can decode all 18 states quite well. And that gives us faith that we can look for replay, i.e. the sequential reactivation pattern of those 18 stimuli. And we only look at the time when they receive the reward, because that is only time the real learning can happen, right? Because anything else is fixed. And when we do that, in general, we can say 2 types of replay. One is the forward replay, again, quite similar as our previous study that picked around 30 or 40 milliseconds and go away. However, intriguingly, we have another type of replay that go in a backward direction and is in a different speed. It's in 150 milliseconds, which is like 6 Hertz also. And this is intriguing, right? Because both in the rodent literature and in our previous studies, we have shown this reverse replay might be related to the value backup. And that is really the function you need to solve credit assignment problem. And from now on, I'm only going to focus these 2 types of replay and at these 2 speed. And you can say this 30 millisecond thing is quite similar as our previous studies. Okay, then we want to test, does this actually similar? Remember, in the first study, we show those 30 or 40 millisecond replay is associated with shape-wave repos, right? So to test that, to test that, one thing we can do is, because in this task, we separate local and non-local learning, right? So we can look for representation content difference for different of replay. We can say, actually, interestingly, the 30 millisecond only care about local experience, i.e. the experience they have, the paths they have just taken. And they don't care about the non-local paths, which are the paths they didn't taken, but nevertheless leading to the same outcome. But the 160 millisecond sequence show a complete different story. It only care about a non-local experience, but not local experience. And then we can look for their physiological difference. Remember, in the previous study, we showed the 30 millisecond thing is associated with shape-wave ripples, and we have replicated that. However, we didn't say that in this study for 160 milliseconds. So here, each of the dots indicating the one of the subject, and the green line in linking the data from the same subject. You can see overall, the subject have stronger ripple power when they are replaying in 30 milliseconds forward versus when they are replaying in a backward direction at 160 milliseconds. And again, just to remind you, this 30 millisecond thing is what we have shown before. And this is quite intriguing. That's basically saying we actually have a different type of replay in this task that really only care about non-local learning and seems doesn't have much thing to do with ripple frequency. And then what is doing them? This is a question we want to ask later. And one idea is this replay might help learning, directly facilitate learning, right? Again, to test that, we can build computational models to direct test this idea. First, again, same as previous, we separate local and non-local learning. And in the non-local learning, we can implement the sequence valuing, right? We can test if we have significant sequence in that trial for that path, do we have increase of learning rate? I.e., does the alpha replay about 0 for 160 milliseconds and do that again for 30 milliseconds, right? And we find only the 160 millisecond sequence facilitate learning, i.e. have a increased learning rate. And that established the second line, i.e. replay indeed facilitated behavior. And this it would be the first time we have established a direct link from neural replay to the behavior change. And this is quite consistent from the previous results we show in the representation content difference, right? Because the only 160 millisecond thing have representation of the non-local path. So by definition, that thing should have certain meaning. And this is showing the meaning of that is to facilitate non-local learning. Okay, and then the last question we want to ask is, does the replay prioritize? Does the replay prioritize based on the theory, i.e. based on the lead and the gain? So the question, translate that question in the data analysis would be, do I see more replay that are leading to yellow in the yellow arm, or do I see more replay in the green arm, right? I can always do this comparison at a trial by trial basis. So to do that, I need to define what is priority. And based on the model, the priority equals to the product of lead and gain. And lead is how often I will encounter this, a gain in future, and a gain is how much actual reward to be gained by replaying that piece of experience. And just to remind you, the lead is manipulated by the starting probability, which is fixed across all the throughout experiment and is learned prior to the main experiment. And the gain manipulation is manipulated trial by trial through the fluctuating of their reward probability. And when I derive both lead and gain, multiply them together and compare them for different paths at a trial by trial basis, this is what I find. I find the sequence difference of in high priority path versus a low priority path, and you can say the blue indicating 30 milliseconds and red indicating the 160 milliseconds. And you can say only the 160 millisecond is prioritized, i.e. you have stronger replay at 160 milliseconds for high priority paths versus low priority paths. And with that, we have established the last line in this triangle, i.e. replay indeed is prioritized and is prioritized based on the long-term model. All right, with that, I can conclude with these 4 triangles that non-local learning is prioritized to support model-based behavior, and the rewards non-local replay at 160 milliseconds help model-based learning. And it's both functional and physiologically different compared to this shape-wave repo, which presumably is this 30 millisecond related replay. And this 160 thing is prioritized for the most policy informative experience. All right. With that, I really want to thank my supervisors, especially Tim Behrens, for the support for all those projects, and also Ray Dolan. And for the first project, I would especially thank Kurth-Nelson, who really is the first one trying to look for this kind of things. And for the second project, I would like to thank Nathaniel Dahl for all the help and interesting discussions, and also for all the amazing collaborators, Elliot Wimmer, Matt Law, and Marcello Mata. All right, thank you very much.
Thank you. That was a wonderful talk. Very amazing what you can do in human. We do have a few minutes for questions, which have come in. So we have one from Carlos Carrasco. Carlos, if you would like to unmute yourself and ask your question, go ahead.
So again, thank you, Yunzhe, for the amazing talk.
Thank you.
My question was in regards to the ripple activity that you showed in the medial-temporal lobe,
Right.
the high frequency activity. I was wondering if you had looked at or thought about looking at cortical brain areas for this high frequency activity. Specifically, I'm thinking of some of the Buzaki lab's work, where they've identified in these rodents these localized ripple oscillations that are concurrent with the hippocampal ripples, specifically in parietal, midline, and prefrontal cortical areas. So I was just curious if, if you have any insight to whether this coupling exists in humans during wakeful rest, like it does in sleep for these rodents, or yeah, just your thoughts in regards to that.
Oh yeah, this is really a good question. Yeah, thank you. So just to clarify, the results I show you here, I should be more precise. So here is not at the high frequency. This is just across all frequencies. So this is a broadband activity. For this analysis, which is the contrast between rewarding sequence and neutral sequence, where I show an increase of the VMPFC, also at the onset of replay, is not necessarily related to the high frequency. So short answer to your question in this data would be, I'm not so sure. But I do know there are some studies in humans actually do look for those kind of coupling, which some people call cross frequency coupling. People say coupling between gamma and theta, for example, between hippocampus and the prefrontal cortex. I haven't looked for that, but I can believe that is true, and that probably can show up in humans.
Thank you so much.
Thanks.
All right. Our next question will be from Yunzhe Liu. If you'd like to ask.
Yes, I'm here. So can you hear me, Yunzhe?
Yes, please. Yes, please.
Yeah, wonderful talk. And I have a very general question that is replay a common mechanism to explain how humans use past experience to guide our behavior? Because in your experiment, the past experiment is kind of rule and knowledge, and you just explicitly to tell your subjects to learn the rule. But what about, and to learn the rule to learn a sequence memory? And what about a more complex structures such as a cognitive map, whose structure is obtained by implicit learning, not a explained learning in your experiment? And because I have read paper on the NC from the lab, which uses HMM to explain the structure transfer of relational map. But this is quite a behavioral experiment with no image data. So I want to know whether the replay is also a candidate mechanism to explain the transfer phenomenon. Do you get what I mean?
Oh yeah, so I think, so our first study is kind of trying to get that, right? So we want to show replay can be seen as a transfer, right? It is transfer of the structural knowledge to the current to the current lower context. So I would say I would think replay would have those functions. As to the question whether replay is the only mechanism for that, I'm not so. Well, that really depends on what is your definition of replay, right? So here I define replay only as a sequential reactivation of different state. But
yes,
you can imagine in some scenario, you only need reactivation, right? You can just reactivate, for example, reactivate the outcome picture with the state, with the picture you want to associate it. And if you do that, you can, in your mind, do associative learning, which presumably is implicit in your definition. So I can imagine that another mechanism to do that. And I think there are another distinctions, as in whether whether we are using a cognitive map, which is like a schema in memory research, i.e., I can using those knowledge to actually generate certain experience versus I actually draw samples from my memory. And for different people, they're using replay differently in those contexts. I think for me, I use that interchangeably. I didn't I didn't make distinction by whether this memory is drawn from a memory pool or is actually generated by some genetic model.
Mm-hmm. Okay, and I'm also curious about that. Why the human brain automatically or implicitly apply the learned knowledge to novel things with shared underlying statistics? I mean, it indeed brings some benefits like generalization or inference, but may also cause confusion if you want to find the dissimilarity, not the similarity. So how do you think about it?
Well, I guess in hippocampus you have both pattern completion and pattern separation, right? So
Yes. Yes.
And you would imagine you have different coding principles for different function, right? For example, for pattern separation, you probably want high sparsity code, right? i.e., coding something in higher dimensions, then you can differentiate that quite easily. So I'm sure the brain have the way to do both of them, and presumably some of those functions is in hippocampus. And I guess it's really about which kind of thing you are asking, right? Because because what memory is one thing. Memory, you can have some overlapping element and some non-overlapping element. But if you imagine you do have a cognitive map, and then that cognitive map, which is a generative model, you can use that models to generate experience and compare them, right? And if that separation is different experience within the same generative model, and then I think you can test that directly. And if they are from different generative models, and then it will become trickier because you need to, in principle, you need to get a handle on the different models they have in the mind in order to answer this question.
Right.
Okay.
Thank you.
Thanks.
Let's move on to our next question. Lennart Lutgau, I would like to ask your question.
Yeah, thanks for the great talk and really impressive work. So I was wondering regarding your second study, whether you could find any evidence for a reduction of basically the decoding probability for the interleaved states between the starting and the final or rewarding, non-rewarding state. Because you could imagine that in the course of learning, and this would presumably also be predicted by temporal difference learning models, that only the final or only the starting stage should actually be assigned with credit, because the interleaved states don't provide any additional information, right, about the reward or non-reward. So did you see anything like that?
Yeah, so yeah, thanks for the question. I think this is a really, really good question. So this actually is, so this is actually the biggest concern when we design this task. As you said, in this task, there's no lead to sequence, right? Because the only thing that matters is the initial state, right? You do one action that you need to the reward, and all the interleaved state doesn't really matter. So that is the major worry we have, i.e. we won't find a replay because they don't need to sequence. But however, interestingly, and also because we have neural imaging data, as you have suggested, we can actually test this idea, i.e. do we only see reactivation when we add the outcome, like say X, do we say reactivation of A1, for example, without a replay of like A3, A2, or as you said, do we actually say D, or like decrease of activation of A3, A2 in the course of learning? Right, so those are really interesting questions, and if that happens, that indicating a change of the state space, change of the representation of the state space through the learning course, which would be remarkable if we can get that. But so the short answer is no. We looked for that. We didn't find evidence for that. But I think it could be because A, they haven't had that many experience, so they haven't able to realize they can have a more efficient representation of the task. As you just said, I just really don't need to representing those intermediate state. I can really just I can only just represent the whole thing as as the bandit task, right? I don't really need those kind of those intermediate state. Basically, we didn't show this evidence, so it could be they don't have enough experience. A second could be because of our experimenters, because in this task we do ask them to always keep the transition thing in the mind, because they are told they're going to be tested of the sequence knowledge in the end. So I imagine those kind of requirements may make the participants always using this sequencing representation. And that might be the reason we didn't say this change of representation that we want to say.
Okay, thank you.
Thanks.
All right, and we'll take our last question, I think, from Alex Park.
Hi, Yunzhe. Thanks for the great talk. I think you already mentioned it, but I just want to check about it. I think the Matter paper actually also suggests that their backward and the forward replay actually came from the same algorithm kind of thing. So I don't know that your data can also support this kind of thing. And I think that even though the backward replay is actually happening in some specific time zone, the reason that they might influencing the behavior maybe it caused by a different mechanism, or it might be just communicated with a different brain area after that. So I don't know how you think about this one. And another small question is that did you find any evidence of like abstraction during the experiments? For example, I don't think that they always need to decode all the 18 states, but maybe they can grouping them together while they're learning the structure better. So did you find any kind of evidence of that? Thank you.
Yeah, right. So yeah, this is a really, really good question. Yeah, I'm actually very excited for because you asked this. So the first thing is about the direction. So in Marchano's paper, the direction is really indicated by whether it's dominated by lead or by gain, right? So if it's dominated by lead, then it's not mostly forward, right? You just do roll out, basically. But if it's dominated by gain, it's most likely to go in the backward direction. And because we are only looking at the reward here, so remember in this task, they are not created equal here, right? Because in this task, only the gain is changing trial by trial, but the lead is remaining constant, right? So that already put emphasis on the rewards part, basically, in that model. So in principle, you can also solve this task rather than at the time when they say the outcome. In principle, you can also solve the task by doing prospective planning at the time when they say, when they need to make a decision, right? At that time, because the SR is different, they are say 1 or D1, and if these are dominant, you should say forward replay, right? As suggested by the Marchano's paper. And when we look for that, we didn't see it. And I think, so we have some guesses. Like one of the guesses would be, in this task, again, as you also mentioned, like planning is not really a major or important rule here, right? As long as you figure out whether X is more rewarding or Y is more rewarding, then you basically solve this task, right? You don't really need to do planning at the time when you are putting different arms. So that this might be a reason we didn't see much of forward replay, like at the time when they need to do planning or at the time when they see the reward, for example. And then to the second question, as do we say the grouping? I think this is a really good question. This is also related to the question the last person have asked, which is all related to the idea of change of the representations. I think the representation, yeah, so I have tests for that. I didn't, so indeed I can decode the sequence code, i.e. D1, D2, D3, or C1, C2, C3 altogether. I can decode that independent from their sensory information. But I didn't say those representations involved in any computation, so to speak. So I didn't say that related to learning. I didn't say that differentiate different like representations. I didn't say that change as the cost of learning. And again, I think one of the reasons that might happen could be because in this task, we do ask them to always remember the sequence relationship and they need to be tested after the main task. And that might put a strong prior on the participant that makes them always want to use this sequence representation.
Yeah. Thank you, Yunzhe. So we're slightly over time, but thank you again so much for coming. And
Thanks.
thank you to all of our participants who are still with us. So we hope to have you join our next seminar. Thank you, everyone.
Thank you.
Thanks.